Hi everyone. So starting from today, we are going to talk about Markov chain. Especially, we're going to talk about the discrete time Markov chain as a special case of stochastic process. Okay. Okay. Then we've learned that a stochastic process is nothing but a collection of random variables, right? And so these are the common stochastic processes. And we've already talked about Bernoulli process and Poisson process. And like I said earlier, starting from today, we are going to talk about discrete-time Markov chain. Okay, so what is Markov chain? At the bottom of this screen, I already described just a little bit. So it's a stochastic model describing a sequence of possible events. In which the probability of each event depends only on the state attained in the previous events. Okay? So the term Markov chain refers to the sequence of random variables such a process moves through with the Markov property, which is the memory list property. You remember that, right? Defining the serial dependence only between the adjacent periods, as in a chain. Okay? Does that make sense? So the key point is when you talk about the Markov chain, discrete-time Markov chain, we need to consider the memory list property always. Okay? Okay. So, like I said, discrete-time Markov chain is a special case of discrete-time stochastic process. We consider a stochastic process x of n that takes on a finite or countable number of possible values. So, in the deterministic Markov chain, the discrete-time Markov chain, if x of n equals I, then we said that the process is in state I at a certain time n. Okay? And the discrete-time stochastic process that satisfies this relationship is known as a discrete-time Markov chain. Okay? And this equation can be interpreted as, for a Markov chain, given the past states, those are x0, x1, x2 through x sub n minus 1, and the present state, which is x of n. The conditional distribution of any future state, which is x sub n plus 1, is independent of the past states because of memory list property. And it only depends on the present state. Okay? So the desired probability, the conditional probability, can be shortened, reduced down to this. Okay? Because the Markov chain cannot remember what happened in the past state. Okay? And here, P sub ij represents the same. The probability that the process will next make a transition into state j when in state I. Okay? Because the probabilities are non-negative, and also because the process must make a transition into some state, we have that sum over j from 0 to plus infinite, P sub ij equals 1. Okay? Okay, so this screen tells us basic concept required for any discrete time Markov chain. So let me just read the screen this time. So consider a system with a finite set of states S1, S2 through S sub n. And the system is observed at a certain sequence of points in time or stages. Okay? And the system may make a transition from one state to another state between observations according to some kind of known probability distributions. Okay? And we assume only stationary transition probabilities. That is, one-step transition probabilities are represented by P sub ij. Okay? And of course, one-step transition probabilities are independent of the time parameter n, which means we assume that transition probability does not change over time. Okay? Keep in mind that. Okay, now let's take a very simple example with forecasting the weather. So suppose that the chance of rain tomorrow depends on previous weather condition, only through whether or not it is raining today. Okay? That is, the chance of rain tomorrow does not depend on past weather condition because of memory release property. Okay? We also suppose that if it rains today, then it will rain tomorrow with probability R, alpha. And if it does not rain today, then it will rain tomorrow with probability beta. So in this case, if we assume that each transition takes 1 day, okay, that is our assumption. Okay, each transition takes 1 day. And if we say that the process is in state 0, okay, so process is in state 0 when it rains, okay, so that indicates rains. And in state 1, when it does not rain, okay, not rain. Then this is a two-state Markov chain. This transition diagram would be like this. So rain to rain is what? Is alpha. It will say if it rains today, then it will rain tomorrow with probability alpha. So starting from state 0 and coming back, state 0 should be alpha, right? Which means it's rain today and it will not rain tomorrow would be what? 1 minus alpha, right? Does that make sense, right? Then what about this? It will say if it does not rain today, then it will rain tomorrow with probability beta. So it indicates that transition probability from 1 to 0 should be beta. Is that right? In other words, 1 to 1 has to be 1 minus beta. Does that make sense? Is that right? But this transition occurs under the assumption that each transition takes 1 day. Okay? And we can also construct one-step transition probability matrix, which is 2 by 2 matrix, because we have only 2 states, rains, not rains, right? So if you say this is 0, 1, 0, 1, then what do we have? It's got to be alpha, 1 minus alpha, and then beta, 1 minus beta. Is that right? And then we can set this equal to P. One-step transition probability P, capital P. You can put exponent 1 if you want, but you can also omit it. Okay? So that is same as just capital P. There is one-step transition probability matrix. Okay? Is that easy? Right? Okay, now let's move on to very similar example. This time we're going to consider one more state. Okay? Previously we only deal with two different states, rains or not rain. But this time we are dealing with three different states. Okay? So let's consider that another forecasting weather example. We suppose that there exist only three different kinds of weather conditions for summer. They are hot, moderate, and cool. Okay? And we also assume that each transition takes 1 day, just like previous example. Okay? So, according to this transition diagram, let's say if today is hot, then tomorrow will be moderate with 50%. Is that right? So here, if today is hot, starting from here. So if today, I should be careful. Okay, so if today is hot, so starting from here, today is hot, then tomorrow will be moderate with 50%, right? Is that right? And let's say if yesterday was cool, like that, okay? If yesterday was cool, then today is cool again with 33%, and so on. Is that right? So let me delete this part. So everybody knows what's going on with this transition diagram, okay? Because we are assuming that each transition takes 1 day, you can get the weather forecast, 1 day weather forecast using this transition diagram. Does that make sense? Okay. So the next thing is, if the transition diagram is given like this, then we can build up the corresponding one-step or one-stage transition probability matrix P. Like this, okay? So let me move this a little bit. So P equals so I'm going to put hot, moderate, and cool. Hot, moderate, and cool. Okay? So starting from hot today, tomorrow will be hot again with 33% of chance, right? Because here, hot to hot is 33%. And then hot to moderate is 50%, right? And then hot to cool will be 1/6, right? Does that make sense? Right? So the same way, you should be able to complete the second row and the third row of the P matrix. Is that right? So let's do that. So starting from moderate today, it can be hot tomorrow with 50% of chance, right? So I write down 1/2. Moderate to moderate would be 1/3. moderate to cool would be 1/6, right? And then lastly, starting from cool, yesterday, for example, it will be cool again today, 1/3. If yesterday was cool, then today will be moderate with 1/3, and then hot with 1/3. Is that right? So I'm going to write down 1/3 each. Does that make sense? Right? So if you suppose today's weather is hot, then obviously the first row number 1 of the matrix P gives the probability distribution of the weather tomorrow. Does that make sense? Right? Okay. Now, we'd like to know that the probability that is cool on Friday, given the weather is hot on Wednesday. Okay? We'd like to know this. We'd like to know the 2-day weather forecast. Okay? We know that 1-day weather forecast can be obtained using this P matrix and this transition diagram. Now we'd like to know the 2-day weather forecast. Okay? That's what you're going to do now. Okay? Okay, actually, I'm going to use new screen. Okay, this is, I need to have a new screen. Okay. Okay. Actually, the desired probability can be obtained, can be computed by conditioning on the Thursday's weather. Okay? So here's the desired probability. Let me write it down first. So desired probability was, we want to know the weather will be cool on Friday, given the weather will be hot on Wednesday. Is that right? And then actually, this probability consists of 3 different cases, depending upon the 3 different weather conditions on Thursday. Is that right? So I'm going to write it down there. It's going to be equal to probability cool on Friday given hot on Thursday times probability, take this, hot on Thursday given hot on Wednesday, plus probability, again, same, cool on Friday. Let me write it down this first. Hot on Wednesday, plus probability, cool on Friday times probability hot on Wednesday. Right? So in this middle, this part this part, this part, this part. Should be 3 different weather conditions on Thursday. Is that right? That's right. So I'm going to write it down. Moderate on Thursday. Moderate on Thursday. Here, cool on Thursday. Here, cool on Thursday. Is that right? Then, what is this probability? That's going to be what? What is this probability? First, what is this probability? It was saying it was hot on Wednesday, and then it become hot on Thursday. Next day, again, it become hot. What is this? That's going to be P sub 1, 1. Is that right? Is that right? That is P sub 1, 1. We are talking about this probability, right? It was hot on Wednesday, and then it becomes hot on Thursday. That's going to be 1/3, which is same as P sub 1, 1. Is that right? Okay, then what about this probability then? It was hot on Thursday, and then next day it becomes cool. What is this? It's got to be P sub 1, 3. Is that right? Are you following me? Right? So it was hot yesterday. Sorry, it was hot on Thursday, and then it becomes cool on Friday. So it is 1/6. Or, in other words, P sub 1, 3. Right? The first subscript is the row number, and second subscript is the column number, right?
I do.
Right? Okay. Okay, now we should be able to do this. What is this? What is this probability? It was hot on Wednesday, and it becomes moderate on Thursday. That's going to be P sub 1, 2. Is that right? How about this probability then? It was moderate on Thursday, and then it becomes cool on Friday. 2, 3. Is that right? So if you continue on, what is this? 1, 3, right? And then how about this? 3, 3. Is that right? Of course, if you use the real number from this one-step transition probability matrix, then it's got to be 1/3 times 1/6, right? 1/2 times 1/6, 1/6 times 1/3. Is that right? Which is same as 0.1944. Okay? So this is the probability of going from state 1, which is hot, to state 3, which is cool. Starting from hot to cool. In 2 stages, in 2 days, starting from Wednesday to Friday. Does it make sense? So So now let's going back to our screen. And actually, if you look at this screen, the same value can be found where? Right here. Okay? So how'd you get this? P-square matrix. How'd you get this? That's exactly what he did. That is the computation. Let me use this. Of P11, P12, 13 times P13, 23, P33. Okay? If you do this, then you should be able to get this value. Okay? And this value, 0.1944, is what? P13. From the square matrix. Is that correct? Right? And then this is how you can get this value. Right? The same. In other words, the same value can be found at row number 1 and column number 3, a p-square matrix that is obtained by this computation. Okay? So, in general, all the information of 2-day weather forecast can be obtained from p-square matrix. Okay? Because the p-square matrix is two-stage transition probability matrix. Okay? So in this example, we assume that one stage means 1 day. Okay? Because there are 2 days gap between Wednesday and Friday. The desired probability can be obtained from this two-stage transition probability matrix. Okay? Does that make sense? Okay, now let's suppose that on Wednesday the weather is hot. Then what is the probability on Saturday? The weather is either moderate or cool. Obviously, starting from Wednesday, Thursday, Friday, and Saturday, how many days? How many days? 3 days, right? So now it's about 3-day weather forecast, right? Does that make sense? Right. So, and the 3-day weather forecast can be found in P to the 3rd power matrix. Like this, okay? So we need 3-step transition probability matrix. So if weather is hot, so starting from the first row of the P to the 3rd power matrix, if the weather is hot, the probability that Saturday, 3 days hence, is moderate is 40.28%, and probability that it is cool is 19.91%. So you can be about 60 point something percent certain that the Saturday will not be hot. Does that make sense? Okay? Okay. Here, the Chapman-Kolmogorov equation provides a general method for computing the n-step transition probability matrix. So we just let the capital P be the one-step transition matrix, then the two-step transition matrix is obtained by multiplying the matrix of one-step transition probability by itself. Okay? And the three-step transition matrix is obtained by computing the third power of the one-step transition probability matrix, P. Okay? So the n-step transition probability matrix, P to the power n, can be obtained by computing the nth power of the one-step transition probability matrix, P. Does that make sense? Okay? Although this concept is very simple, this is very important. Okay? So just keep in mind that. Okay, so any questions so far? It's not hard at all, right? It's pretty easy, straightforward. Okay, now let's talk about long-run behavior of Markov chains. One of the main applications of Markov chain is in the finding the long-range predictions. Okay, so the long-range predictions are always possible with regular transition matrices. So the concept of regular transition matrices is very important. Okay? So to discuss about long-run behavior of Markov chain, we need to know the concept of regular. So like this screen shows, a Markov chain is regular if for some positive integer k, here the keyword is some, okay? I'm not talking about for every positive integer value of k. I'm not just talking about only one value of positive integer k, okay? It's got to be some value, okay? For some positive integer value of k, p to the power k matrix has strictly positive elements only. Okay? So in other words, if some power of the transition matrix contains all positive entries, the transition matrix is said to be regular. Okay? So let's take some example. Okay, let's take this example. Okay. Okay. So we are talking about the simple transition matrix. Okay. So let's say let me rewrite down. Let's say this is the matrix A. So we have 0, 1, 1, 0. So obviously this matrix A is not regular, right? Because we have 0 values right here and here. Is that right? So this is not the all the elements of this matrix A is not strictly positive. Is that right? So this is not regular. But what about this? A square matrix. It's going to be 1, 0, 1, 0, 1. Okay? And then A to the third power is going back to original matrix, 0, 1, 1, 0. Which means A to the fourth power is same as A square matrix, 1, 0, 0, 1. So looks like it just oscillate between these two. Okay? So in the end, I'd say a to the power of 2n matrix is same as 1, 0, 0, 1. A to the power 2n plus 1 becomes 0, 1, 1, 0. Okay? So as you can see here, a to the power k matrix always has some 0 values in it. Is that correct? Right? Always it has 0 values in it. So we can say that this is not regular. Okay? This is not regular matrix. Does that make sense? Okay, now let's take another example. What about this case? Let's take this case. Okay? So we have 0, 1, 1, and then 1/2, 1/2, and all other values are 0. So we are going to write it down. So here, A matrix is 0, 1, 1, 0.5, 0.5, 0, 0, 0, 0. Okay? How about if we square? Then what do we have? It's going to be 1, 0, 0, 0, 0, and then 0.5, 0.5, 0.5, 0.5. Okay? And then, actually, if you continue on doing that, A to the power 2n matrix is always same as A square matrix, 1, 0, 0, 0, 0, 0.5, 0.5, 0.5, 0.5. In other words, A to the 2n plus 1th power matrix is always same as original matrix A, 0, 1, 1, 0.5, 0.5, 0, 0, 0, 0. So obviously, since A to the power k matrix, for every value of k, we always have some 0 values, right? So this is not regular matrix either. Does that make sense? Okay? Now let's take another example. What about, let's say, we have A matrix. Matrix A is 0, 0, 1, 2/3, 0, 1/3, 1/2, 1/4, 1/4. So currently we have 3 0 values on it, right? Now let's square a matrix, then it's going to be 2/3, 0, 1/3, 1/6, 3/4, 1/12, 7 24, 9 16th, And then we have 7/48. Okay? Now, if we have a to the third power matrix, we're going to see that all of its elements are strictly positive. Those are 13/24, 3/16, 13/48, 43/96, 23/64, 43/192. See? In this matrix, all of elements are strictly positive. All of elements are greater than 0. Okay? So this indicates that this original matrix is regular. Okay? Of course, if its transition matrix is regular, then of course the corresponding Markov chain is regular Markov chain. Okay? Just simple concept. Okay, so if a Markov chain is regular, then there exists a limiting probability, okay, that the process will be in state J, let's say J, after a very, very large number of transitions. And that value is always independent of the initial state. See here, this is the limiting probabilities, or the long run, the steady state probability, I'm sorry, okay? See, if you look at this, pi j does not contain any information about the initial state, I. Is that right? So I'd say this limiting probability is always independent of the initial state. Keep in mind that. And this limiting probability, pi j, is called the steady state probability. So limiting probability, steady state probability is the same meaning. Okay? Okay, so going back to the summer weather example we just talked about. So this n value gets larger and larger. So this is the P matrix, P square, P to the power 3, P to the power 4, 5, 6, 7, 8, 9, 10. Okay? So this value of n gets larger and larger. P to the power n matrix gets closer and closer to this matrix. Okay? And of course, these values are independent of the initial state. Okay? See? It really doesn't matter if you start from the weather is hot, you have the same probability values. 0.4, 0.4, 0.4. For the next weather becomes hot, right? And then, of course, if you start from moderate, you will land on hot weather with same probability, 40%. If you start from cool, again, the weather, next weather will be landed on cool with the same probability. Okay? So all of these values are independent of the initial state. Does that make sense? Okay. Now we notice that if you multiply certain probability distribution, let's say 1, 0, 0, to that steady state probability, then you're going to get this value, right? If you multiply different probability distribution, then you also end up with same result. What about this? If you multiply different probability distribution for the weather condition, of course, those are hot, moderate, cold, hot, moderate, cold, hot, moderate, cold, right? These are hot, moderate, cold, right? Whatever values, whatever different transition probability distribution you multiply, then you are going to end up with same result. This should be same as this. Okay? What about this? If you multiply ABC, of course we are dealing with probability distribution. The summation of A plus B plus C got to be 1, right? Just like this. 0.5 plus 0.3 plus 0.2 is 1. 1 plus 0, 0 is 1. 0 plus 1 plus 0 is 1, right? What is this value? That's going to be A times this times the first column, right? What is that? 0.4 times A, B, C. Is that right? And then next column, if you multiply this times this, it's the same. 0.4 times A plus B plus C. Is that right? How about the next value? It's going to be ABC times the last column, which is 0.2 times A plus B plus C. Is that right? Of course, if you take out ABC, then it's going to be A plus B plus C. I just take out this value. What is left over? 0.4, 0.4, 0.2. Is that right? And I just mentioned that summation of A, B, C should be 1. So what is this value? It's 1. Is that right? So we have 0.4, 0.4, 0.2. Is that correct? Right? So we always get the same value. Is that right? Does that make sense? So this is our conclusion. No matter what A, B, and C's are, the answer is always 0.4, 0.4, 0.2. Okay? Are you following me? Right? So, can I move on? Next screen. Okay. So we may say that no matter what assumptions you make about the initial probability distributions, after a large number of steps have been taken, the probability distribution is approximately this value, always. Okay? Remember that when n value becomes large, this p to the power n matrix gets closer and closer to this matrix. Okay? Now, the question is, how could we determine this without computing large powers of P matrix and estimating the steady state matrix. We notice that the probability distribution 0.4, 0.4, 0.2 has property saying that this, right? Always we come up with same value. In other words, a solution of the matrix equation, of this matrix equation, is same as this, okay? And this part can be expressed by pi p equals pi in matrix form, okay? So this is, I'd say, pi, and then this part is p, then this part becomes pi, okay? So we can find the steady state probability matrix 0.4, 0.4, 0.2 by solving pi's like this. And keep in mind that summation of all of these pi values has to be 1 because we are dealing with probability distribution, okay? And what is this part again? That's going to be pi times p equals pi. Is that right? So this whole part is pi, this whole part is p, then this part becomes pi again. Okay? In matrix form, of course. So we can come up with this conclusion. The limiting probabilities must satisfy these 3 conditions. Okay? That is, limiting probability is the unique non-negative solution of these 3 conditions. Okay? So keep in mind that this is very important. Okay? This is one of the key points of today's lecture. Okay? Because we are dealing with probability distribution, summation of those pi is going to be 1, right? And then we know that how we derive this formula, right? I just showed you. And then each pi value is going to be greater than 0. Okay? Right. Okay. So let's go back to the weather example, summer weather forecast example. So we are going to use this one-step transition probability matrix, and then we're going to compute limiting probability distributions, okay, which is pi's. Since there are 3 different states, we're going to use either pi h, or let's use pi 1. Just pi 1, pi 2, pi 3. Okay, so we have 1, 2, 3, 1, 2, 3, like that. Okay, so we're going to determine pi 1, pi 2, and pi 3. Okay, using these 3 conditions. Okay, that's what I'm going to do. Okay, we're going to use Cupid. So I'm going to use new screen. So I'm going to write down the original matrix. Let's use, okay. Our P matrix, I'm going to use different color. P matrix is 1/3, 1/2, 1/6, 1/2, 1/3, 1/6. 1/3, 1/3, 1/3. Okay? So first I'm going to use pi equals pi p in matrix form. Okay? So it's going to be pi 1, pi 2, pi 3 times, pi 1, pi 2, let me write down here. So it's going to be, I should write down this way, pi 1, pi 2, pi 3 is equal to pi 1, pi 2, pi 3 times P matrix, right? Which is 1/3, 1/2, 1/6, 1/2, 1/3, 1/6, 1/3, 1/3, 1/3. Okay? Is that correct? So we have 3 equations from this, right? The first one, what is pi 1? Pi 1 is going to be pi times the first column of P matrix. Is that right? So it's going to be 1/3 pi 1, 1/2 pi 2, 1/3 pi 3. What is pi 2? Pi 2 is equal to pi times second column of this pi P matrix, right? So it's going to be 1/2 pi 1, 1/3 pi 2, 1/3 pi 3. Is that right? How about pi 3? That's pi times the last column of this P matrix. That's going to be 1/6 pi 1, 1/6 pi 2, and then 1/3 pi 3. Is that correct? Right? But I got to tell you that this system of linear equations are linearly dependent. What does it mean? One of these 3 equations is redundant. Why is that? Because if you add up left-hand side, what is this? Pi 1 plus pi 2 plus pi 3. Is that right? If you add up right-hand side, it's also pi 1 plus pi 2 plus pi 3. Okay? So if you add up these 3 equations, it just tells you nothing. Pi 1 plus pi 2 plus pi 3 is equal to pi 1 plus pi 2 plus pi 3. It's nothing, right? Which means we got to choose.
We can't find value.
Right. Okay, hold on. Which means we got to choose arbitrarily one of these equations. So let's choose the last equation and then discard it. Okay? You can choose the first equation or second equation if you want. Okay? It really doesn't matter. You just need to choose one of those 3 equations arbitrarily and then discard it. But we have one more condition. What is that? Summation of pi 1, pi 2, pi 3 is equal to 1. Is that right? Since we have 3 unknown variables, which is pi 1, pi 2, pi 3, and then we have 3 equations. So technically, you can find the solution for this linear system of equation. Does that make sense? Okay? So that's what you need to do. Cool. I can extend the equation. So let's say this is equation number 1, and this is equation number 2. And then pi 1, 2, 3, summation of those three values are 1. Let's say this is equation number 3. Okay? So we're going to use these three equations to obtain the limiting probabilities distribution, pi 1, pi 2, pi 3. So we're going to multiply 6 on both sides of this equation number 1, multiply 6, and then we're going to also multiply 6 on both sides of this equation number 2. Okay? That's what you're going to do. Then we have what do we have? 4 pi 1 minus 3 pi 2 minus 2 pi 3 equals 0. Is that right? I just multiply 6 on both sides and then move all of this right-hand side to the left-hand side. Then we come up with this. Is that right? So let's say this is 1 prime. How about the second equation? After you multiply 6 on both sides, move right-hand side to the left-hand side. Then we're going to come up with negative 3 pi 1 plus 4 pi 2 minus 2 pi 3 equals 0. So let's say this is 2 prime. Okay? So if you move 2 pi 3, this, so if we move this part to the right-hand side, and then move this part to the right-hand side, then we know that 4 pi 1 minus 3 pi 2 equals negative 3 pi 1 plus 4 pi 2. Is that correct? Right? So from here, we know that 7 pi 1 equals 7 pi 2, which means that pi 1 is equal to pi 2. So we use this in the equation number 3, which is pi 1 plus pi 2 plus pi 3 equals 1. So here we use this. Then here we have 2 pi 1, okay? Because pi 1 is equal to pi 2 plus pi 3 equals 1. So let's say this is the 4. Then up here, from up here, 1 prime becomes pi 1 minus 2 pi 3 equals 0. So we have pi 1 equals 2 pi 3. Is that right? So 4, equation 4, this one, becomes 2 times 2 pi 3 plus pi 3 equals 1. So we have 5 pi 3 equals 1. So we know that pi 3 is 1/5. Is that right? As a result, we know that pi 1 is 2 times pi 3. So it's got to be 2/5, right? Which is equal to pi 2. Does that make sense? So definitely pi 1 and pi 2 are 40%, and then pi 3 is 20%. So I would say in the long run, summer day will be hot or moderate with probabilities 40% each, right? And then the weather will be cool with probability 20%. That's how you can interpret this limiting probability value. Okay? Like I said, in the long run, like maybe 100 years later, even 1,000 years later, let's say the weather condition becomes stable. And then when you check your weather condition, this limiting probability saying that the weather will be moderate with 40% of chances, and the weather will be hot with another 40% of chance, and then weather will be cool with only 20% of chance. Okay? So I believe we have already answered this question. What fraction of the future days will the weather be hot? It's 40%. Is that right? From the limiting probability or steady state probability, which is pi 1 in our case. All right? Okay, thank you. So this is all for today. And like I mentioned, we're going to invest pretty good amount of time for the discrete time Markov chain. And then I will try to give you a lot of examples, okay, of this concept. Okay, thank you. I will see you next time. Bye-bye.